Welcome back. What I would like to do in this second half of the lecture is to discuss how we can expand the applicability of the method of maximum entropy of the methods of entropic inference to answer a particularly crucial question, uh, which is, suppose you're trying to figure out a posterior, but by maximizing an entropy. That's what we want to do. Uh, if the entropy maximum is very, very, very sharp, it's almost intuitive clear that you have a good posterior there, whatever maximizes the entropy. But what if the entropy maximum is very, very shallow? To what extent are you sure that those probability distributions that are almost at the maximum are supposed to be ruled out completely, right? That's the kind of question that we would like to answer. And what's really amusing is that we're going to answer that question using the method of maximum entropy itself. So to see how that goes, let us draw pictures. So this is what we want to do. If this is the space of all probability distributions, so this is a statistical manifold of many, many dimensions, infinite dimensions, and this is the prior, and I give you a constraint. What we do is we rank probability distributions according to entropy, and we select the one that the probability distribution that obeys the constraints but has maximum entropy. So the way we would go about doing that is we maximize the entropy, and here's the entropy, P log P, and these are Px's, right, over Qx, some prior, and subject to whatever constraints we have. Very good. In order to analyze what's actually going on here, let me take this constrained subspace, the space of all probability distributions that satisfy the constraint, and let me enlarge it. And so what I'm going to do is I'm going to enlarge that space, and this is what it looks now. I made it bigger. And here's the prior outside, somewhere out there. And when we maximize the entropy, we land on that posterior, the posterior that the probability distribution that maximizes the entropy is going to be somewhere there. In some sort of sense, it's the one that's closest to the prior. So it's somewhere there. Well, okay, so our question really here is, how about probability distributions that are over there? So let me redraw this. In order to analyze what's going on this statistical manifold, so let me write a name for it, the statistical manifold of constrained distributions. The goal is to pick one out of this whole space. In order to analyze what's going on there, given that it is a statistical manifold, I'm going to introduce coordinates. So here are the coordinates. You introduce as many as you want, as many as your constraints allow you. And let us assume that this is the point theta 0, the posterior that maximizes entropy. So this gives a posterior Px. The posterior is going to be, of all of those probability distributions that we had before, it's the one that's labeled by theta 0. Otherwise, a generic point theta gives you a probability distribution Px of theta. something, any point there. Point theta in this space represents a probability distribution in that submanifold. Very good. This space we're going to call capital theta. It's this thing that looks like a football. And we would like to know if we draw the surfaces of equal entropy over there, we would like to know what happens if this maximum is not sharp. How do we take into account probability distributions that are close to the maximum? So this is the kind of problem that we are going to figure out now. And the way we handle it is by saying, look, I know that the method of maximum entropy has led me to a posterior that maximizes preference. Good, we know that. But to what extent should I believe that this is the best choice? To what extent should I believe that neighboring distributions are good choices? When I phrase it like that, to what extent do I believe that the value theta is the one I should pick? You realize that this, what we are looking for is we're looking for a probability distribution on the space theta. For a probability distribution on the statistical manifold capital theta. And this is what this is going to be. It's going to be a probability of theta. That's what we want. Clearly, we want, if we do things right, what we should see is that the value of theta that gets preferred when we analyze this problem ought to be precisely theta 0. After all, that's what the method of maximum entropy gave us. But how much do we prefer that theta 0 over all the others? That's what we want to find out. Very good. How do we handle this? We're going to use the method of maximum entropy. So what we're going to do is maximize an entropy, choose a prior, choose constraints, and proceed from there, right? So this is an inference problem. So what we're going to do is first recognize that the whole idea behind doing this problem was to figure out a probability distribution for x. But now we're looking for probability distributions for theta. Not only is x not known, the theta that describes probability distributions in this region are not known either. So the universe of this course, the space in which we're carrying out our inferences, is not just the space of x's, but the space of x's and thetas. What this immediately means is that what we're going to try to maximize, or what we want, is a joint distribution of x and thetas. And in order to find this joint distribution, let me write it as capital P. This is what we want, right? In order to find this distribution, we maximize the entropy of the joint Now it's lowercase. Relative to the joint prior, which is minus dx d theta. Now here I'm going to write p j x theta log p j joint x theta divided by the joint prior. Very good. So that's the first piece of business. What are we talking about? We're talking about x's and thetas, and that's the corresponding entropy. Second piece of business, the prior. Figuring out what the prior is sometimes a big problem, because what we're asking is, what did you know before you knew the constraints? What did you know before you knew the information that became available? So you have to be able to separate those two steps. So before we know what the constraints are, namely that the probability distributions that make up the family of the constraint surface are functions of this form, right? Before we knew that, what did we know about x and theta? We definitely, let me just write it, did not know anything that related them. Before we knew that theta was a parameter in probability distributions, we knew nothing that would connect x and theta. And so basically we have a product of two distributions. Let's call them like that. So this is before, let me write it down. Before we know the connection between x and thetas. It's a product. Telling you x doesn't tell you anything about theta and vice versa. Now, what do we pick for x? In the case of x, it's easy because the prior for x is whatever we used when we maximized this entropy to find the posterior at theta 0. Okay, so that one is easy. So this is the same old qx is the same that we had before. The crucial question is, what is this guy? And here we do have one piece of information about these guys here. And the piece of information that we have is that whatever those thetas are, they are meant to be parameters that label distributions in this larger space. They're parameters. They label distributions, and therefore it makes sense to say. So we know that the space of thetas is a statistical manifold. Given that that is the case, it makes sense to say that q theta, the theta is uniform. We're going to assume that we're maximally ignorant about what theta is. So it's a statistical manifold. If we claim maximum ignorance, we pick that the distribution q thetas is uniform. On what space? On whatever space the constraints might actually give us. And so what this means is that q theta is proportional to the volume element in the theta space. So what this tells us then is that whatever this joint prior is going to be proportional to the prior for x's, whatever that was, multiplied by the determinant of the information metric. Very good. So now we're making some progress. This is the object that goes down here. How about the constraints? 3. The constraints. Well, whatever this joint probability distribution is, we can always write it as some probability distribution over theta multiplied by the probability distribution of x given theta. And now at this stage, we are actually going to say, we're going to constrain this. We're going to say that this probability distribution is precisely the same probability distributions that defined the statistical manifold of the constrained distributions. So what we're saying here is, I give you a prior, I give you a constraint. Okay, what is that constraint? Oh, okay, these are going to be Gaussians with variance such and such, mean values such and such. Okay, those Gaussians of variance such and such and mean value such and such, we're going to figure out what is the whole space, and we're going to give coordinates for them. Maybe they're Gaussians, maybe these are mean values, maybe these are variances, whatever they are, we have the parameters. At this point, we know what these functions are. We do not know which one we're supposed to pick, but we know that these are Gaussians or multinomials or Cauchy distributions or whatever. So the constraint, this is known. Okay, so this is the constraint. These functions are known. So that's a constraint, and that's it. We substitute. So what we're going to do is we're going to vary the entropy. This is the free object we want to compute. So we're going to vary the entropy with that specific form. Therefore, what the entropy looks like is, let's just write it out. There is going to be a p theta, px given theta, log p theta, px given theta, that's the joint. And under here we have q, did I do this right? We have the g1/2 theta and then multiplied by qx. That's the prior. Very good. Please notice that this constraint that we're using here is not in the form of an expected value constraint. The method of maximum entropy does not in any way place any limitations on the kind of information you're allowed to process. You give me information, it becomes a constraint, you use it. In this particular case, we're going to maximize this expression, but we do not, since we do not have expected value constraints, the method of maximization cannot be using Lagrange multipliers. So how do we handle this? Well, the first thing we can actually do is, let's simplify this expression. Notice that the log of a product, you have a bunch of products here, separates into a sum. So just let's rewrite it. Here we go. We're going to rewrite it. Minus dx d theta p theta p x given theta, and let's write the first piece. And now let me write the second piece. For the second piece, I'm going to rewrite this as the integral d theta p theta, those two terms, and then here I'm going to write minus the integral dx px given theta log px given theta over qx. Very good. This can be simplified further. We're going to, let me write this down here. For the first piece, the first term here, we notice that these terms just depend on theta. These terms just depend on theta. And this term here is the one that depends on x. It's the only one. And if we integrate over x, this drops out by normalization. So the first piece that we have there is minus d theta p theta log p theta divided by g to the 1/2 theta. So it's very interesting. This is just a standard entropy, a maximization of entropy in this space capital theta. It's just, come on. There we go. It's just maximizing an entropy in this space. That's what we're going to be doing. But then we have this other term here. And when you look here, what we have is d theta p theta and the object that we have here is the entropy of the variable x, of the distribution px, but for each value of theta. So whatever this guy here is, that's a function of theta. It is essentially the entropy that was being maximized when we maximize this object here, subject to the constraints that you're going to be on this space. In fact, this actually makes me think that maybe it's best if I put a j there so that we don't confuse this joint entropy with this entropy here. So let me write this as Sj, joint entropy, and so this is joint entropy. And this guy here is S theta. So this is like you see, it's the expected value of the entropy of the distribution Px given theta taken over the whole space theta, but with no Lagrange multiplier there. Very good. So now we are going to vary delta p theta to find and impose that the variation of this guy is equal to 0. And then we're done. Okay, when we vary this expression, I'm going to have to come back and forth here. What we get is going to be that the variation delta Sj is supposed to be 0, and this is what we're going to write as there is going to be an integral over the theta, and then here this is going to be the variation b. So when we do the variation of this delta p, what we're going to get is the minus log p over g. Minus log p theta over g to the 1/2 of theta. Then we vary this p here. with delta p. So we take the derivative of the log. It's going to be 1 over p. It cancels that. And so we're going to have then just the delta p. The variation of g is 0 because this does not contain p, right? So that's just going to be a 1. Then there is going to be, of course I forgot, right? Didn't I forget? We want to vary this with a normalization constraint. Well, we better include that. P theta equals 1. So we better include that in our variation. Then there is going to be an alpha delta p for normalization. And finally, there is this last term here in which we vary that delta p. Here there is no p theta at all. It disappeared. It's only one in front. So the only other term that appears is plus s of theta. Now we complete the whole calculation by setting that equal to 0 because these variations are all independent. And so the result is going to be that the log of p theta divided by g to the 1/2 is going to be 1 plus alpha plus s theta. And so take the exponentials, and what we're going to get is g to the 1/2 exponential, take the g to the other side, then we have e to the s theta, and there is going to be 1 plus alpha. Let's just call that normalization, the exponential of that, where zeta is the integral over all the thetas, the volume element in the theta space multiplied by s theta. Very good. This is the result we seek. The probability, let me rewrite it. The probability that the value of theta lands within the small interval d theta is going to be given by 1 over zeta, the exponential of the entropy within that statistical manifold. And then here we have the volume element. This is the result we want. Notice this is a volume element. It is invariant under changes of coordinates. The entropy is also invariant under changes of those coordinates. And this is also a scalar. It's a total probability within a certain region. So whatever you might say about an expression like this, one of the wonderful things is that it's totally clean. It's completely invariant under complex transformations. Given that this is a volume, it is the volume on this space theta of the constraint surface. Given that that is a volume, then this object here is a scalar density. This is a scalar. It is invariant under changes of coordinates, but it is also a volume in that it is the probability per unit volume. So this is the probability per unit volume. And this is just, except for a normalization, it's just the exponential of the entropy. Now this is very nice because it's definitely clear that the value, the preferred value of theta is theta 0, that maximizes the entropy is theta on the space theta. So it's a good consistency check. If you use the method maximum entropy to find the point of maximum entropy, to find the posterior, and you're asking for how less likely is it that you should have chosen neighbors, then your conclusion is supposed to be that, well, it should be less, right? Well, that's what we're finding here. The value that is preferred is indeed the maximum entropy. But now look at this. It means that if you have an entropy that's really a very sharp maximum, if S has a sharp maximum at theta 0, then the probability distribution that we have there is something that is a very sharp function at the point theta 0. So what that means is that this is approximately something like a delta function of theta 0. Now if S theta has a shallow maximum, nothing prevents you from having entropies that could actually be just flat, right? So under those circumstances, you see that values of theta away from theta 0 can actually make an important contribution. Very good. Then values of theta away from theta 0 can contribute significantly. So let's go back to the original problem. The original problem was to find a probability distribution for P which for P that satisfy the constraints. But now we see that this is not such a good idea. This is a good approach to what the posterior ought to be if your entropy has a sharp maximum. If the posterior is not sharp, if the probability distribution of theta is not sharp, it's much better to actually say, look, whatever expression you find for x, it should be obtained by taking the joint posterior of x and theta and marginalizing over theta. And in this case, we know what this is. This is going to be d theta, the joint posterior. You can read it from up here. Is going to be the probability, the posterior for theta, and then these are the functions that make up the constraints. So this is going to be the probability of theta, and here we're going to have the constraint functions, and we're going to write this, the new A better posterior for x is going to be d theta g1/2 theta, the entropy here, the normalization, and then multiplied like that. If this guy happens to be a delta function, right? If these guys here happen to be a delta function, then you see you're back to selecting the posterior you had before. If not, well, this is a better estimate of the probability for x. So what this has allowed us to do is to improve the method of maximum entropy for situations in which the maximum of the entropy is not particularly sharp. Very good. With this, we conclude our formulation of the method of entropic inference. What we're going to be doing next is extracting some further juice out of these constructions and do some physics. Before I pass on to that, it probably struck your imagination that saying that when you maximize an entropy, you get S theta 0, and the value that is preferred is theta 0. Yes, but if you're away from the maximum, it's exponentials of the entropy. This is the Einstein formula for fluctuations, for thermodynamic fluctuations, which we have derived in a much more general setting of just asking, okay, you are going to prefer the maximum entropy, but how about the others? The others are fluctuations, okay? And this is the Einstein formula. So it's very nice to have a method that both allows you to take general information, general constraints into account with general priors. So it unifies maxent with base. And then it also unifies with the Einstein theory of fluctuations in the case of thermodynamics, but now we can do it in general. See you next time.